Start the recording here. We're looking at section 6.4 now. We're going to learn something called the Gram-Schmidt process. What I want to do here to sort of get started with 6.4 is I want to draw two vectors okay, and I'm going to call the vectors x1 and x2. Okay, and over here I'm going to draw, hold on, I don't know why it just doesn't take sometimes. All right, I'm going to draw two vectors. Okay, I'm going to draw two vectors. Hold on. Okay, two vectors, v1 and v2. Okay, and where do x1 and x, well, let me be a little more clear here. I'm going to call, I got the span of x1 and x2 here. Okay. And what is the span of x1 and x2 equal to? I mean, I can tell you what it is, but, and notice x1 and x2 are not orthogonal. The span of x1 and x2 equals what in my little picture here? R what? R2. That's right. Because I'm drawing in two-dimensional whiteboard here. Two-dimensional whiteboard. Okay. All right. Now let me go over here to the right. Let me ask you about the span of v1 and v2. What's the span of v1, v2 equal to? R2 as well. That's right, Solomon. We're in this whiteboard, two-dimensional whiteboard. So the reason well, first, are there any questions on that? You have to let me know if you have questions. All right, the reason I'm doing this is we have vectors. The span of vectors is some subspace. But when the basis vectors are not orthogonal, as in the vectors x1 and x2, theoretically, should it be possible to find vectors v1 and v2 that are orthogonal and span the same space as the vectors x1 and x2 do? Should that be possible? In theory, it should. And as a matter of fact, let me show you how you can do this. Let's work with this first picture here. Let's work with this first picture. And maybe what I'll do is call this, no, I'll keep it as x2. Hold on. Let's say, so I only want you now to focus on, this side. Don't worry about over here. Hey, it's lovely, but don't worry about that. What if I wanted an orthogonal basis, but I wanted to hold on to x1. x1, oh, and I should have vector signs here, right? I want to keep x1. That I want to keep. But I want a vector orthogonal to x1. But that is in the plane that x1 and x2 are in. Okay, we can get that very easily. There it is. Right? So the point is from this, and we're going to get to our example. It's a right angle there. I'm trying to draw a right angle. I don't know why it's complaining. Come on, right angle. So and maybe I would call this, V2. The point is whenever you have a subspace of vectors, you can construct an orthogonal basis that's of vectors that spans the same space as your original vectors do. X1 and x2, let's say we're not even talking about r squared. Let's just say x1 and x2 span some space. Okay, well, but you would agree that the vectors x1 and v2 span the same space as the vectors x1 and x2 do. So we can basically construct a orthogonal basis. Okay, let's go to an example so that we can make this clear. Are there any questions on this? All right. Let's go to the example here. Okay, we're going to use something called the Gram-Schmidt process. And where do these vectors live? X1, X2, and X3. Where do these vectors live? They live in R4. Okay. What's the dimension of the span of these vectors, X1, X2, and X3? What's the dimension? So dimension is a number. Good. It's going to be 3. It's a three-dimensional subspace. These vectors are linearly independent. Okay. All right. Let me give you a moment to copy this down, and then we'll work through this problem. Okay, so we're going to use, we have here, again, we have three vectors that are linearly independent. They live in R4, but the span of vectors x1, x2, and x3 forms a three-dimensional subspace of R4. Are the vectors x1, x2, and x3 orthogonal? Are they orthogonal? No, definitely not. The dot products are not equal to 0 between the vectors. So what we're going to do, but you see, when we create this orthogonal basis, we have to be assured that this orthogonal basis, that the span of the that the span of the basis vectors in our orthogonal basis must span the same space as the vectors x1 and x2 and x3 do. The subspace spanned by these orthogonal vectors we're looking for has to be the same subspace as the span of the vectors x1, x2, and x3. So here's how you do this. First of all, you pick a vector. Okay, you're gonna go. What we're gonna do is we're gonna be going from the basis v1, x1, x2, x3 to a new basis with new basis vectors v1, v2, and v3. Okay, so v1, v2, and v3 are going to be our new basis vectors. Okay, and we have to find them. Well, you know, I'm going to just, I can let one of the vectors in my original basis be v1. Okay, I can do that, you know, and then I got to find an orthogonal vector. So what I do is I define w1 to be the span of this vector x1, which is, by the way, the span of v1. And then I construct an orthogonal vector v2. I construct it. So look at the illustration here. I draw this w1. Gee, you know, the subspace w1 appears to be aligned. Why is w1 aligned? This space w1 appears to be aligned, right? Now it's aligned in R4. That's right, Matthew. It's the span of only one vector. It's a one-dimensional subspace, right? We have one vector. All right. So, all right. So what I do here is I draw x1 and I draw x2. And it's clear that the space, well, it's clear that, hold on, I might put this in maybe green. This vector v2, okay, is orthogonal to x1. And I'm going to ask this too, as a little aside here, is the span of x1 and x2 let me draw this right. 2s and 3s are sometimes hard to write, is the span of x1 and x2 equal to the span of x1 and v2. Is the span of the vectors x1 and x2 equal to the span of the vectors x1, sorry, is the span of the vectors x1 and x2 equal to the span of the vectors x1 and v2? Is the two-dimensional subspace spanned by x1 and x2 equal to the two-dimensional subspace spanned by vectors x1 and v2? It is. I mean, just think of it, pretend, I mean, look, think about the plane, the plane here that you see on the screen. The vectors x2 and x1 span that plane. Well, the vectors v1, which equals x1, and v2, don't they span the same plane? Don't they span the same plane? They do. Absolutely. Okay, so it doesn't matter if the vectors are in R. I mean, I'm just intuitively speaking, they do. So, hey, I'm going to find out what this vector v2 is and add it to my vector v1. So the vectors, so this is yes, by the way. And so I'm going to find out what v2 is, and I'm going to find that vector v2, and I'm going to add it to my vector v1. Hey, at least then I'll have two orthogonal vectors. It's better than having no orthogonal vectors, right? Now, I won't have the whole space yet, but I'll have some of the space, so to speak. So, okay, v2 would be x2 minus the projection of x2 onto v1. Hold on, wait. Question here. V2, well, V2 and V1, the span of the vectors V1 and V2 is equivalent to the span of the vectors X1 and X2. That's what I, yeah, that's what I mean. I hope hopefully I said that, but that's what I meant. Okay, so now to find V2, well, we know how to deal with vectors. You know, if we take x2, and you know, here's my let's see, I'm gonna clear that. Here's x2. Here's my projection vector right here. There's my projection vector. So if I negate the projection vector, okay, then that's going to be the negative of the projection vector will be, you know, this vector here. And so the negative of the projection vector plus x2 will equal v2, tip to tail vector addition. And we know how to find the projection of x2 onto subspace W1. We learned this back in section 6.2, right? We learned this back in section 6.2. There's the formula. And you know, and incidentally, the projection of x2 onto subspace W1 would have to be, and that's the blue vector. That's the blue vector that I've drawn. Of course, it's a multiple of the V1 vector. Of course, it's a multiple of the V1 vector. Okay, so I mean, sometimes students kind of get a little bit confused about what vector to put there, but hey, the picture helps you a lot. The projection of x2 onto the subspace W1 is a multiple of the V1 vector. You can see it based on the picture. And so we work it out. And the projection, this vector V2 is going to be this vector of fractions. The vector -3/4, a fourth, a fourth, and a fourth. Okay, so let me know if you have any questions up to, you know, that part there. Let me see. Well, you're defining W1 to be the span of x1. So what's a projection vector? You take the vector x2 and you smash it down into the subspace. That produces this blue vector here. That blue vector is the projection of the vector x2 onto subspace W1. Okay. We don't have W2 yet. We will, but we don't have it yet. Now here's the thing. This vector V2, you know, I got it. -3/4, a fourth, a fourth, a fourth. But I like to work with vectors that are easy to work with. Would it be okay, instead of using vector V2, could I use V2 prime? That doesn't mean derivative, it's just V2 prime. Would vector V2 prime, which is -3, 1, 1, 1, would that vector be okay? Yeah, I just multiplied. V2 prime is 4 times V2. It's a multiple of V2. So, in other words, you know, I'm constructing my basis. I'm constructing my orthogonal basis. So far, you know, I'm keeping x1. And the next vector, well, I got to pick V2 or V2. I could pick V2, but why not pick V2 prime? Why not choose that? Because, you know, it's still, V2 prime will still be orthogonal to x1. Okay. Well, do we have our orthogonal basis yet? Are we done? Not yet. That's right, because x1, x2, and x3 form a three-dimensional subspace of R4. I only have two vectors. I need another vector in here, you know, to get a three-dimensional subspace. So I'll show you how we get that. May I move to the next page? All right. All right. Okay, here we go. All right. So, and actually going back, that what I had here, I mean, my basis so far, actually, I'm calling it, I had x1 there, but it's v1, v2 prime, right? Because x1 equals v1. I mean, I want to get away from the x's and work with the v's, So I have v1 and v2 prime, and now I'm looking for the third vector. Okay, v1, v2 prime, what would the third vector be? Okay, well, again, a picture helps a lot. So now I have this subspace W2. Subspace W2 is going to be the span of V1 and V2 prime. And by the way, that's the same as the span of X1 and X2. It's the same two-dimensional subspace. And now in the picture, I'm drawing a vector X3. X3, well, I'll let you copy down the picture and then we'll talk about it, okay? Let me give you a moment here. The reason we use the V2 prime is because V2, the vector V2 had fractions in it. And I wanted to pick a multiple of that vector V2. So I went 4 times V2 to get V2 prime. Right. Okay. Good question. Okay, so now we got a nice picture here. We got a nice picture. Thank you. And okay. So the vectors v1 and v2 prime are orthogonal. Notice how I draw the right angle in there, right here. Just helps me a little bit. And they lie in this space W2, subspace. And X3 is drawn outside the subspace because it's clear if you at that X3 is not it's not contained in the subspace spanned by X1 and X2. Okay, you can't write X3 as a linear combination of an X1 and X2. So X3 has to be drawn outside the subspace. So do you see that, I mean, we agree that X1, X2, and X3 form it's a three-dimensional subspace of R4. Well, V1, V2 prime, and the vector V3 here, they also span the same space. Okay, so if we can find out what V3 is, we'll be good. Well, you can see here the projection of the vector X3 onto subspace W2. The vector V3 is just going to be X3 minus the projection of the vector X3 onto W2. That's what it's going to be. And so, again, the vectors V1 and V2 prime are orthogonal, so we can get that projection vector using our formulas. I want to make sure I'm pacing myself. Solomon, you're doing all right? Okay, good, good. All right, well, you know, this is just computational stuff, No big deal. Give you a moment. Okay, and so we just go through the work. You go through the work. All right, and I get to here, and then we have to add those. We have to add those two vectors together. Those two vectors with the fractions in. I know in linear algebra, you know how to add fractions, right? So not a problem there. I'll go to the next page when you're ready. Is anybody still copying? Sega's good, all right. Okay, Solomon needs just a little more time. Okay, all right, that's fine. Christy's good. Masha's good. Okay, Matthew and Solomon. All right, let's go to the next page. Kevin's good. All right, here we go. So I combine those two vectors and then I take the difference between the two vectors, and again I get another vector v3 with fractions in it. So I'm going to choose then a multiple of that vector v3. And so we note that the span of, and there should be a prime here, right? Hold on. Sometimes hard to get this stuff. Okay, so the span of V1, V2 prime, and V3 prime is equivalent to the span of our original three vectors. You see, we have to preserve the subspace. You see, we have to preserve it, and we did. And we did. And so we have our orthogonal basis, which is V1, V2 prime, V3 prime. Let me Are there any questions? All right. All right. Well, that's the Gram-Schmidt process, and this was actually laid out in the book here. Let me see here. Let me just find the process in the book. We did example one. We worked through example one, and what I'd like to do is bring the formal process up in the book, just so you can see the theorem. Now, incidentally, we have an orthogonal basis, but we could always make that orthogonal basis an orthonormal basis, right? By normalizing our vectors. We can always do that. So we can always do that. That being said, all right, let me go ahead then and bring up the textbook, if that's all right. Here. This is the Gram-Schmidt process that we just went through. Okay. And we did it where we had a set of three vectors. Okay. So in your homework, you're going to have to construct an orthogonal basis where you have two vectors, three vectors, and I'm going to give you one with four vectors. Okay, that'll take a little time, It's an extra step, right? But it's good for you to see it. Sorry about that, Christy. I was kind of debating it, but I think you should see it. When I took my linear algebra, I took a linear algebra exam in college. I had to do one, do a Gram-Schmidt process, I believe, with 4 vectors. Hey, and I got it right too. But I remember having to do one like that. You know, by the way, when you yeah, I mean, it could have been 3, but I think it was 4 vectors, Matthew, because I remember it, and I felt so happy getting it right on my timed exam. You know, when you get your vectors, when you get your answers at the end, you know, I'm thinking about the exam, you know, you do a problem like this. Let's say you get your vectors. Is there anything you could do to check your answer before you submit your answer for a problem like this? You know, when you get your new vectors, when you do a Gram-Schmidt problem, is there anything you could do to, what could you do, Solomon, as kind of a check? Do the dot product, do the inner product. That's right, Robin. That's right, Solomon. Check to see if the dot product equals 0 between your vectors. Or you can probably manually see it too. You can manually look at 2 vectors and do the dot product in your head, right? All right. So let's continue on here with section 6.4. Okay, so you can get, or if you can get an orthogonal basis, you can get an orthonormal basis. I'm not worried about that. But there's something called QR factorization that is important you to be aware of. Let me see here. Hold on. Let me just move this over, make this a little bigger. Okay, one moment here. So hold on. Okay, there was our Gram-Schmidt process, right? QR factorization of matrices. So if you have a M by N matrix A with linearly independent columns, then applying the Gram-Schmidt process with normalizations, that means the vectors have unit length, to the vectors amounts to factoring the matrix A, as described in the next theorem. This factorization is widely used in computer algorithms for various computations, such as solving equations, and that'll be talked about. We'll talk about that on this coming Tuesday's class, section 6.5. And finding, okay, so what is this QR factorization? Well, it's theorem 12. Okay. If you have an M by N matrix with linearly independent columns, then the matrix A can be factored as A equals Q times R, where Q is an M by N matrix whose columns form an orthonormal basis for the column space of A, okay, and R is an N by N upper triangular invertible matrix with positive entries on its diagonal. It's called a QR factorization. So you already have seen a factorization of a matrix. You learned about diagonalization, where you take a matrix A and write it as P times D times P inverse. That's a factorization of a matrix. Well, this is another factor. Of course, that's for a square matrix. This factorization is for an M by N matrix, so it's a general factorization. Let me see, there's a question here. Oh, yes, that's right. Thank you, Matthew. LU factorization as well. That's right. So these factorizations are very handy. Um, for instance, being able to write the matrix A, diagonalize the matrix A, allows you to compute the matrix A to high powers, A to the 100th power, big matrices, and it can be done easily with that factorization. Well, QR factorization is going to have its advantages as well. They give a proof. I don't necessarily want to go through the proof, but you can look at it if you want. I want to look at an example here. With the example, hopefully things will be a little bit intuitive. So here, what they do in example 4 is they want you to find the QR factorization of this matrix A. Now notice the matrix A here, the columns of the matrix A are the same as the example we just did. The column vectors of that matrix A are the same as the vectors that the same vectors, those column vectors, as the example that we just did, which is example 1. So they say, okay, here are your vectors v1, v2 prime, and v3. And v3, for some reason, they chose to let v3 stay as the fractions, but I like v2 prime better, because the matrix Q, the columns of the matrix Q consist of the vectors, the orthogonal vectors that you get with the Gram-Schmidt process, but they're normalized, so they have length 1. And for v3 prime, we had 0, -2, 1, and 1, and it's much easier to get that third column in the matrix Q if you have integers for your third vector. But are you okay with the matrix Q? Are you all right with the matrix Q there? Okay, let me see. Hold on. Okay, well then let's figure out then what the matrix R is, because we know what Q is. We know that A equals Q times R, but we have to find what R is. So let's go. It takes some work, Matthew. This will take some work, and you know that for the exam, I'm going to ask you to work out computations by hand on these kind of problems. But I'm not so you want to you want to, but there aren't going to be, since it takes time. I have to be aware of that. But it is helpful, and many of you have told me it's helpful to work out linear algebra by hand when you can, because you can lose the feel if you don't. You can lose the feel if you don't, right? And it's just all right. Don't worry, Christy. The work will be manageable. Don't worry. But all right, so let's now head over to here. Now, by construction, all right, we have the matrix Q. A equals Q times R. We're looking for the matrix R. Notice that Q transpose times Q equals the identity. Okay, because your columns of Q are orthonormal, and if you in the matrix Q is Q is m by n. If you do Q transpose times Q, that's going to be an n by m matrix times an m by n matrix. So you're going to get an identity matrix that's an n by n. Okay, you're going to get an identity matrix that's an n by n. And again, what happens is when you have orthonormal columns and you take Q transpose times Q, some of those products are going to equal 1, because the dot product of 2 unit vectors is going to equal 1. So that'll get you the diagonal entries for the identity. And then the other dot products are going to equal 0 because the vectors are orthogonal. So therefore, Q transpose times Q equals the identity. So if you were to, hold on here, now one moment. Now we're looking at Q transpose times A. So if you take Q transpose times A, remember A equals Q times R, then Q transpose times A is Q transpose times QR, but Q transpose times Q is the identity, and that's how you get R. So that's what they're doing here. That's how they're getting the matrix R. Okay, so, and notice the R matrix is a 3 by 3 matrix, as it should be. Okay, are there any questions on this QR factorization? All right, they always have numerical notes. They mention here that when the Gram-Schmidt process is run on a computer, round-off error can build up as the vectors are calculated. You've already seen round-off error in the first MATLAB assignment when you had to do a check on, you had to solve AX equals B, that system with X equals A inverse times B, and then when you did a check, you weren't getting exactly the 0 vector. When you did AX minus B, you weren't getting exactly the 0 vector. There's round-off error that results when you compute an inverse. And you can imagine there's round-off error that will occur here as well. They you know, talk about these different, there's a different computer-based QR factorization. MATLAB will have has a QR factorization algorithm, but it's not going to produce the answers that MyMathLab's going to want. MyMathLab's going to want you to use the Gram-Schmidt process to construct your matrix Q. Okay, so that's how you should be doing it, right? Because you're learning. Okay, that's basically section 6.4. Are there any questions on that? All right, one thing I'll mention too, you notice here in the matrix R, they have square roots. Okay, so you know MyMathLab wants exact R, doesn't want decimals, and you know I'm going to want that. But the square root of 12 in this matrix R, they don't write that as 2 root 3. Okay, and I know that sometimes, like, just based on like when I create the assignments and I look at the, you know, kind of sample problems and the homework, they sometimes want simplified radical form, and sometimes they don't seem to worry about it. So, you know, I think it's good to have things in simplified radical form, but you could try getting your answer without simplified radical form. But then if it doesn't work, maybe use simplified radical form. I'm just saying. Has anybody noticed that maybe in the homework where it didn't accept an answer because in a problem because you didn't have it in simplified radical form? Has anybody seen that in the homework yet? Or like, I mean, all right. Well, if you haven't, maybe it's not a concern. But let me go ahead and stop. It needs to be simplified, Solomon. So simplified, you mean like square root of 12 should be 2 times the square root of 3? If you can break it down, you should break it down. Okay, all right. So like if you had the square root of 59, you wouldn't have to break that down. But the square root of 12, you would need to write as 2 root 3 in MyMathLab. Okay, all right. Very good, very good. Let me stop the recording here.